today we're going to do a similar problem to the last tutorial, except we're going to bump the area of steel up from 300 millimeters squared in the bottom to 500, which is above AS balance technically. But the truth of the matter is, as long as we keep the difference between upper and lower steel, 500 minus 200, below 362, then that also in effect is below row balance. That's something to always keep in mind. If you have tension, if you have compression steel in the section, you would take the difference between the 500 minus the 200. So we're still below row balance in this case, because our steel is 500 minus 200, which equals 300 millimeters squared, which is less than 362. Okay, so what we first do is calculate the stresses or the forces in the steel compression, so the forces in the stress block, which would be phi m x 0.85 f prime m, and then the force in the steel. We'll assume everything yields, and then we'll check this condition by looking at the strains using similar triangles. Alright, so let's work out the force in the steel prime, Fs prime. So that would be 0.85 times the area of steel prime, which is the top steel 200 millimeters squared, times, we're assuming it yields at 400 MPa. So that would come out to be 0.85 times 200 times 400, 68,000 newtons. Then the force in the masonry would be phi m 0.6 times the stress block factor x 0.5 times 0.85 times 10 MPa, f prime m is 10 MPa, times the width times a, the height of the stress block. So we don't know what the height of the stress block is. It's to be solved. But so we take 0.6 times 0.5 times 0.85 times 10 times 190. So that's 485 A, and that would be in newtons. And then the force in the steel, and the tension steel, it's also 0.85 times its corresponding area of steel, 500 millimeters squared. And again, we're assuming the steel also yields 400 MPa. So it's 0.85 times 500 millimeters squared times 400 MPa. It's 170,000 newtons. So we could balance the forces. We know that these forces, force in the steel compression and the stress block are both in compression, and then this is in tension. So we'd write out 68,000 newtons plus the 485 A, that's the stress block, is equal to 170,000 newtons. And then we could solve for A. So 170,000 minus 68,000 divided by 485. A is 210. And the C then would be 210 over 0.8, right? Be 263. Okay, now that we have the forces, we can check our assumption to see if the steel actually did yield here and here. So we know that the C value we just calculated here is 263. So we can use similar triangles to solve for the strain in the steel prime and the compression. So that would be C is to 0.003. What C minus this distance, which is 60 millimeters. C minus 60 is to strain the steel prime. So we can solve for that directly. We can say 263 over 263 minus 60, and then take 0.003 divided by that answer. Strain the steel 2.32 times 10 to the minus 3. So that's 0.0023 2, and that's above 0.002, which is the yield strain of steel. Right, the strain yield of steel is 0.002, and so long as we're above it, then the stress is 400. And we could do the same for the bottom steel. Now we could say C is to 0.003. What this distance here, which is D minus C. So D is 590 minus C is the strain in the steel. So we can calculate that now. We know that C is 263 divided by 590 minus 263. And then we take 0.003 divided by that. So that's also well in excess of 0.002. That's 0.00373. So this also implies that the steel has yielded, and this 4 MPa assumption is valid. So that's great. Now we can go on to find out what the moment resistance is. Moment resistance will just be, we could take forces about here. We could take force about anywhere, but this would be a convenient point because we won't have to use the lever arm associated with this force at 0. So moment resistance is the force in the steel prime, which is 68 kilonewtons, times its distance from here to here, which is D minus 60. D is 530 minus 60, plus the force in the mortar and the masonry. We kind of calculate 485A. So 485A is 485 times 210, which is 102,000 newtons. So 102 kilonewtons times depth minus A over 2, because the stress block is A. So D is 530 minus 210 over 2. Now we can solve for the moment resistance. So 68 times 530 minus 60 plus 102 times 530 minus 210 over 2 divided by 1,000 puts in the kilonewton meters, so 75.3 kilonewton meters.